Welcome to this video on load flow analysis. In this video, we shall continue with our learning outcome number 2, that is load flow solution. In this video particularly, we shall deal with example on load flow using Gauss-Seidel method, and I will start with simple problem, that is including only PQ buses. So here is one example is given. It is a 3-bus system. The first bus, it is a slack bus, and as we have discussed, the voltage is specified here, that is 1.05 at an angle 0. Now at this bus we have to calculate what is the real power and reactive power that is to be injected from this bus into the from the generator into this bus. Bus number 2, it is specified as PQ bus with P value, that is power, reactive power, it is 256.6 megawatt, and reactive power it is 110.2 MVAR. So at this bus we have to calculate the voltage, that is what is the value of V2, magnitude as well as its phase angle. Next, at third bus, it is also given, it is specified as PQ bus, and the value of P, that is active power, it is 138.6 megawatt, and the reactive power it is given 45.2 MVAR. At this bus we have to calculate the value of voltage, that is V3, magnitude and its phase angle. So in the load flow using Gauss-Seidel, as we have discussed in earlier video, that the first objective is to find the voltages. So this voltage is already known. We have to calculate V2, that is voltage at bus number 2 and the voltage at bus number 3. Then after getting the voltage, then the line current, line flow, then bus power and bus current, they are calculated. So we shall see it by step. Now the first step in the solution, we have to form a Y bus. Y bus, it is a bus admittance matrix, and in the present problem, now it is 3 by 3 bus. Y bus, it is a bus admittance matrix. Now in the present problem, it will be 3 by 3. This Y bus, we can form it by either inspection method or by singular transformation, but I will form it by inspection method because there is no mutual admittance between the lines. Now we have to find out the element of this matrix. The first element is Y11, next Y12, Y13, Y21, Y22, Y23, Y31, Y32, Y33. Now let us find out these elements. I will first find out the diagonal elements, that is Y11, Y22 and Y33. Now Y11, it is the total admittance connected to bus 1. So this is our bus number 1 to which these two lines are connected, this line and this line. The admittance of each of this line is given Y12 and Y13. So we have to add these two admittances, that is Y12 plus Y13. Y12 is 10 minus J20, that is already given. Sometimes if they give you impedance, then you have to convert it into admittance. Y12 plus Y13, Y13 is 10 minus J30. Now we can add them. 10 plus 10, it is 20, real part is added, then imaginary part is 20 and 30, so it is 50. This is Y11, 20 minus J50, more value. Similarly, Y22, it is the total admittance connected to bus number 2. Now this line and this line, they are connected to bus number 2. So we have to add their admittances. So it is Y12 plus Y23. So Y12, it is 10 minus J20 and plus 16 minus J32. So we will get this value as 26, adding the real part and then adding the imaginary part. Minus J, please note down this is minus. So it is 32, it is 52 over here. This is more value. Similarly, let us find out the third principal diagonal element, that is Y33. So total admittance connected to bus number 3. So these two lines, they are connected to bus number 3. So we have to add their admittances. That is Y13 plus Y23, which is equal to 10 minus J30 plus 16 minus J32, which is equal to 26 minus J62 more. Now let us calculate off diagonal elements Y12. I will first calculate Y12, and already we know that Y bus, it is a symmetric matrix. So Y12 and Y21 will be equal. So I can write it as Y2 Y21, which is equal to, now what is Y12? Y12 means the admittance connected between bus number 1 and 2, and this is the line which is connected between bus 1 and 2, and the admittance is 10 minus J20. So we have to take the admittance Y12 and we have to put negative sign to that. So Y12 is 10 minus J20. So it is minus 10 plus J20. Similarly, let us calculate the admittance of diagonal element Y13. Y13 will be equal to Y31 because of the symmetry. So it is equal to minus Y13. So Y13, it is equal to negative of the admittance between negative of the admittance of the transmission line connected between bus 1 and 3. Between 1 and 3, this is the admittance connected. So it is minus 10 plus J30. Then the last element is Y23, and because of symmetry, it is equal to Y32, which is equal to negative of the admittance of the transmission line connected between 2 and 3. Between 2 and 3, the admittance is 16 minus J32, so it is minus 16 plus J32. That all values, they are in mhos. So this is how we can form Y bus by inspection method. It is very, very simple. So diagonal element of this matrix, they are the total admittance connected to a particular bus, and the off diagonal element, they are the negative of the admittance of the transmission line connected between the respective buses. So this is step 1. Now let us go to step 2. So now we have to calculate the voltage. So now for this problem we have to calculate voltage V2 and voltage V3. And what we have to start? To start with the solution, as already we have discussed, we have to make the assumptions. So assume voltages for PQ buses. So second bus and third bus are PQ buses. Already the voltage of the first bus is known. So we will make an assumption here. V2, we are assuming it as 1 plus J0. That is 1 magnitude and angle 0. We are assuming this voltage in per unit. Similarly, voltage at V3 is assumed as 1 at an angle 0, that is 1.0 plus J0. This assumption of 1 at an angle 0 for both the buses, it is called as flat start. It is called as flat start. And for most of the practical examples, this is fair enough to start with this flat start. After assuming the voltages, now we are assuming V2 here as 1 at an angle 0. This is not the correct value, this is our assumption. And V3 also we are assuming as 1 at an angle 0. This is also not the correct, but it is our assumption. So we are always starting with assumption in numerical analysis, as we have discussed earlier. Now we have to calculate the correct values. Calculate voltages at PQ buses. They are more accurate values, not exact values. They are more accurate values. So what is the equation for calculating V2? This equation, it can be obtained from our voltage equation already we have derived. Vi is equal to 1 divided by Yii in bracket Pi minus Jqi divided by Vi conjugate minus summation k is equal to 1, k is not equal to I, and now n up to n, it is Yik into Vk. So this is the equation already we have derived in previous video. Now in this video we are calculating voltage at the second bus, so we have to take I value as 2, and the present problem, it is 3 bus system, so we have to take the value of n as 3. So substituting I is equal to 2 and n is equal to 3, expanding the summation, we get this equation. Now we have to substitute the values. Now here P2, this is P2 value, that is the active power at second bus, but you note down here it is written as minus 2.566. So how do you get this minus 2.5? 2.566, it is per unit. Remember, all the parameters, all the terms in the equation, they are in per units. So this is 256.6 divided by base. Base is assumed as 100 MVA. It is uh, fair to assume this base value, even though it is not mentioned in the problem, but we can assume 100 MVA as the base value. So 100 divided 256.6 divided by 100, it will be 2.566. Now, as we have already discussed, this P value at this point, that is Pi, it is the net active power injected into the bus. So we want the active power to be in this direction. But now we are given that we are taking a power from the bus, but we want what power we are injecting into the bus. So it is minus 2.566 because of this direction, reverse direction. Similarly, this Qi value, that is Q2 value, it is converted to base, and again we are putting minus sign to that, so it should get the net reactive power injected into the bus. Then expanding this summation and putting other admittance values, we get this voltage at second bus, and this is more accurate value. We have made assumption 1 and 0, but we are now getting the more correct value as 0.9825 minus j 0.310. So all of you please use your calculator to compute this value of voltage. You see that you get this voltage. Okay, and now on the same background we can calculate voltage at the third bus. Again, now here we have to put in this equation, now we have to put I is equal to 3 and number of buses in the system as usual it is 3, and again here this P3 value it is taken as 1.386. Now it is divided by base and it is found in the reverse direction. Similarly, for Q, it is divided by 100 and again it is to be injected into the bus. So, after substituting P3, Q3 voltages, admittances, then we get this voltage V3 as 1.011 minus J 0.353. Now, we have obtained the voltage at all the buses. Now we have to check, that is step number 4, whether we have to stop our iteration or what, that is check for convergence. So now you calculate the magnitude of this voltage V2. I hope it will be around 0.98, and even this magnitude V3 we will get it is around 1.0011. Now find out the maximum of this. The maximum, uh, now we have to find out the difference vector. So the difference vector V2, it is equal to V2 calculated minus assumption. So this is our first iterated value and our assumption is 0. So we get 0.98 minus 1 around 0.02. Similarly, if you calculate the difference vector for third V3, then V3 magnitude at the first iteration minus V3 assumption. So we will get it as around 0.001. Now, if these difference values of the voltages V2 and V3, if those values delta V2, delta V3, if these values are less than some tolerance, now here tolerance, if we assume 0.1, if it is assumed 0.1, then we can see that the difference are not less than 0.1. Then the value what we have calculated, they are not correct values, we have to go to the next iteration. In the case if the difference vector is, if the difference voltage is less than 0.1, if it is less than 0.1, then we have to stop the okay. Now in the present case, I think no, it is okay. I will assume this 0.001. Okay, so tolerance is 0.001. So our difference is not less than 0.001. We have to go to the next iteration. But if the difference now in the present case, the difference is more than 0.001, so we have to go to the next iteration. But I will not go for the next iteration. I am telling you here in step 4 we have to check for the convergence. If the difference of the voltage, the present calculated value and the previous assumed value, if the difference is less than some tolerance, then we have to stop, or else we have to go to the next iteration. Once this conversion criteria is met, then we have to go for performing the load flow. So in this load flow, what are parameters we are calculating? The first parameter is the line currents and line flows. So I'll just give you the equations how to calculate the line current. Now here we already know the voltage V1, V2 already we have calculated. Now we can calculate the current. Say the current is I12, that is the current from bus 1 to 2, it is equal to, the potential difference is V1 minus V2 into admittance. The admittance is Y12. Then we will get the current. So in this way we can calculate the current in all the lines of the given system. Then how to calculate the line flows? Line flows, say S12, it is equal to Now I call it as I12 is the line current and S12 is the line flow. So S12 is equal to V1, the voltage at bus 1, into I12 conjugate. So this will give you the line flow from bus 1 to 2. So in this way, we can calculate the line current and line flow in all the lines. After calculating line current and line flow, then we have to calculate the loss. What is loss in the system? Suppose S12 is the line flow from 1 to 2 and S21 is the line flow from bus 2 to 1. Then the loss, I will call it as loss in the first transmission line, it is equal to S12 plus S21. So we will get the loss, and here we will get the active power loss as well as reactive power loss. So here we can see what calculations are made. S12, it is a line flow from bus 1 to 2. This is the active power flow from bus 1 to 2 in megawatt, and this is 84.0 MVAR. It is the reactive power flow from bus 1 to 2. Similarly, S21, the line flow from 2 to 1, 191 is the active power flow and 67 MER is the reactive power flow. Now, if you add S12 plus S21, then we will get the loss, active power loss and reactive power loss in the system, that is L1. So, here you can see 8.5 megawatt is the active power loss in this transmission line and 70 MER is the reactive power loss in this transmission line. Once we get this, then we have to calculate the burst power. So, what is burst power? So, burst power, it is S1. S1 is equal to S12 plus S13. S12 is the line flow from bus 1 to 2, and here will S13 is the line flow from bus 1 to 3. Then adding these two line flows, we will get the total power that is at this bus, which is equal to, now we get active power as 409.5 megawatt and 189 MVAR. So after calculating the bus power, we can calculate what is the bus current. So S1 divided by V1 and its conjugate, we can calculate what is the bus current at a particular bus. So once the voltages are calculated through iterations, once we get the final voltages, the correct values, then line current, line flow, losses, bus power, bus current, they are calculated. So altogether, these all parameters, they is called as load flow. Okay, so this is how we can perform load flow using Gauss Seidel. Here only I have considered PQ buses. In the next problem, I will consider PV bus, and we will see how the problem gets modified, what calculations we have to do. In this video, up to this only. Thank you very much.